Right. So the basic idea of the analysis of the map network was to see if by somehow developing, if you like, some kind of language for processing the map, could you sort of step by step find individual bounded regions. And the language that I've used is based on two function types. Okay, one of them is called from, and the other is onto. Now, the basic idea behind these two things is if you have an individual line, for example, I'm going to select this line here, so we're going to start off by actually hiding all the lines here except L0. Hide, right? So all these red dots are actually where individual lines connect with another line. So here, if we zoom in, these two dots, these two red dots are where two other lines connect with L0, which is this line here. So we zoom out. Reset view. Okay. Now, what we want to do is we just want to see a subset of these lines. So we're going to start off by selecting L7. Right. So L7 is one particular line, and I know that from studying this map intensively that L7 has 3 lines that connect from it, and these lines are L8, which is that line, L9, which is that line, and L10, and that line. So if we zoom in, we just pan a little, so we can see there we've got 3 connections, and each one of these is a different line. So that's L10, that's L9, and that's L8. And the idea behind the sort of the language that I'm using to analyze this network is to work on this idea that if I have a line, you can either have lines connecting from it, in which case that's what we have with L7, or you can have lines connecting onto a particular line. In this case, these 3 lines, L10, L9, and L8, connect onto this outer line, L0. Okay, so what I'm going to do is that's the idea, if you like, graphically. And what I'm going to do now is I'm going to step into the command line and show you this programmatically by calling the different functions and giving the results out. Alright, so I'm just gonna go through briefly the terminology that I was using, both in writing the code but also in trying to understand this, trying to understand the map and trying to expand what works for a small bounded region and trying to expand it over the entire map of Jamaica. Okay, so the first thing that I defined was this primary line, this red line. I decided to start by calling this stem line. And if you think of a river system, the stem line would be the main river channel, and to and from that you would have tributaries, and that's where these blue lines are. So these, blue line 1, that's L10, L9, and L8. These are tributaries of L7. And these tributaries then feed into another line. In this case, they all feed into the same line, which is L0, this outer line. And I tend to call this a terminal, or in a river system, that might be another stem. But for the purpose of the analysis process, we just call this a terminal to distinguish it from the original terminal. So you've original stem line. So you've got a stem line L7, and you've got the tributaries L10, L9, and L8. Okay, so that's graphically. We're going to have a look at this now from a sort of a command line perspective. Right, so we're going to start off by loading up that particular map that we've just been looking at. So that's St. Elizabeth. So we're going to load up St. Elizabeth. Essentially what that line says is give me all the data for St. Elizabeth, and in particular we want the CO variable, which is just the coordinates that make up that map. Indies is just a variable that stores the indices of connections, which all these red lines, these red dots, and adj is just a variable that contains the adjacency matrix, which tells me which lines connect onto which other lines. So in this case, which lines connect onto L7, and from that, what else do they connect onto? Now, to explore a little bit more if you like, the language of analysis, I defined these two key methods that I used to find these bounded regions. The first one is called from. Right, from takes 3 input parameters. The first one is the line, so in this case we're interested in L7, and the second are just indi, which is indices, and adj, which is the adjacency matrix. And from this, if we call that, it tells us, right, from L7 we get line L8, and we get L9 and L10. That's in the second column. So the second column is just the label of the lines that we are interested in. And if we go back to the graphical map, we can see that yes, we have that. We've got L10, L8, L9. Right, to make this a little bit easier, I'm going to dock this chart so we can see the command line and the graphic. The command line and the graphic more easily. Okay, so there we go. So. Right. Okay. So again, we've just instructed the program to go through and tell us which lines come from L7, and it returns L8, L9, and L10, which we have here. So we've got L10, L9, and L8. Right. So that's one half of the approach to understanding this shape. The other bit was, okay, if we know which lines come from a particular stem line, in this case L7, it would also be particularly useful to tell me, if I have a particular tributary, where does that tributary connect onto? Okay. Now, before doing that, just need to just outline these other variables inside this data. Okay, so we said that the second column contained the labels. The first column contains what are called the tip type. Now, the tip type tells me what particular whether it's a head or a tail connection on the particular line. So on L7, if you look at any particular line, one end is a head, the other end is a tail. So according to this, it's telling me that L8 is connected to L7 and is connected at the tail. Same thing with L9, same thing with L10. That's what this T variable indicates. If they were heads, it would be an H in place of the T's. And the third and fourth columns indicate particular node indices. This is where these individual nodes, this head or tail, where they occur in the particular vector that contains all the line coordinates. In this particular variable is called CO. So CO is a variable that contains all the coordinates and is telling me that coordinate 2138 is line L8's tail. So if we scroll down all the way down to 2138, 2136, right? 2136 is right, 2138, that is L8's tail. And if we want, we can very quickly see that on a map. Scatter. Scatter. So we want to plot the CL, and we want so 2138 is the particular index, so we can write this down. We got 2138 column 1 of CO, and we want to plot the y-axis, if you like, the latitude value, and that's in column 2, and that's again 2138. Let's see what that does. Okay, if we go back into our figure, right, so you see here we've got this little dot here. The other half of the map analysis language that we're using was onto, and the idea behind this was if I'm on a particular tributary line, for example L10, and I wanted to know what it connects onto, is there some kind of call that I can issue, and it can return the particular line that joins onto the end of L10. Right, so to do this, we define something called onto, and it takes a minimum of 3 input parameters. So we're interested in L10, so we say L10, and we want to know where the head of L10 connects to, because this last call tells us that we already know that the tail of L10 is connected to L7, so we want to know where the head of L10 connects to. So we issue that L10 head, and we need to pass in another parameter. This is indi, which tells us the index, and we say, right, return. Oh, right, why has that not worked? Oh, actually, that's incorrect. What you need to do is, in order to find the onto connection for L10, actually it's not indi, you need to pass the adjacency matrix. So we're just going to modify that. Adjacency matrix. Right, it tells us that L10 connects to L0. These two methods, from and onto, is it possible by having a series of calls either from or onto, sort of sequentially called, can I somehow then generate this bounded region? So for example, I'll be starting on L7, issue the from call, get L10, and then from L10 issue the onto call, get L0, and from that issue the from call again to get the next line, and so forth, in order to generate the bounded region. That's the basic idea of the analysis algorithm. Okay, now that we've got this, what's the basic idea of the from and onto calls, perhaps now is a good idea to actually see this working. Okay, so we're going to clear a command line, CLC. We've already loaded the data. We know that we are on map St. Elizabeth Parish. The first thing we have to do is we have to get some idea about the fingerprint of the entire map. Okay, so we're gonna reselect all the lines so they're visible. Ooh, we've just hidden them. Make them more visible. So we've got our map restored. All the lines are the same thickness. Now the first thing we have to do is we have to get some idea about the type of map ID that we have, and this map ID is just a representation of the type of connections that I have. So every map is different. So this one's got a different number of lines. This one has got 17 lines. This one has 14, St. James. This is Westmoreland. This has 19 lines. This is Manchester, and this has 18 lines. And in each one of those lines, you're going to have different types of connections. So, for example, L7 in St. Elizabeth has got 3 lines coming off it. If we look at L7 in for St. James, it looks like, oh look, it doesn't have any lines on it. So can we somehow get an overall picture for the map ID, and from this can we then start some kind of steps towards getting an idea of the different lines and what else they might be connected to. So since we're working with St. Elizabeth, to do this we just issue a fingerprint call. So fp is equal to fingerprint. So this call is just a function that goes through and it just calculates what the fingerprint for a particular map is. So we do that and we get a fingerprint value. And again, these columns all represent parameters of the particular map. So for example, the first column tells me which of the lines have connections on them. So L0, this line here, has got lots of connections. It's got this is L1, L2, so on and so forth. And second column is just the count of the number of connections on the line, and the third column is another count, but this is the count of number of non-duplicated line connections. A duplicate is, for example, if you look at this line L1, you can see that it's connected at one end to L0, but also the other end is connected to L0 as well. So that's a duplicate. So if I wanted to count the number of non-duplicated lines, it would miss out L1. And this fourth column contains some amalgamation of what those actual lines are, rather than just the count.